In this video, I'm going to talk to you about energy and power. So here's an overview of what I'll be talking about. Now, the first thing I'm going to talk about is work done. The definition of work done is that it's the energy transferred to or from an object via the application of a force along a displacement. And the equation is that work done in joules equals force in newtons times distance in meters. Okay, so if we look at an example here, we've got an object of mass 5 kilograms that's pushed 2 meters across a surface with a force of 24 newtons. And the question is, how much work is done? So we've got the equation, work done equals force times distance, put the numbers in, and we see that the work done is 48 joules. That moves us on to conservation of energy. So conservation of energy is a fundamental concept in physics. It states that energy cannot be created or destroyed in an isolated system, and that energy can only be transferred from one form to another. And the total amount of energy in a closed system remains constant over time. Conservation of energy is vital in many areas of physics and engineering, and it shows that if you track all forms of energy that go into the system and out of the system, a sum of all that energy will balance. In any process, energy cannot just appear out of nowhere or disappear. It must always be accounted for in some way. Okay, so here's another example. An object of mass 5 kilograms is lifted from the floor onto a bench 1.2 meters above the floor. And again, the question is how much work is done. So we have work done equals force times distance. The force in this case is mass times acceleration. So acceleration due to gravity we're going to take as 10 meters per second squared. And so we do 5 for the mass times 10, and we've got 50 newtons. So that's the force of gravity pushing down on the object, and we have to oppose that in order to move it up 1.2 meters. So the work done is 50 times 1.2, gives us 60 joules overall. But where did that energy go to? So remember we just said energy is conserved, and so where that energy went to is the subject of the next slide. So that energy was actually transferred to gravitational potential energy. And that's the energy an object possesses because of its position in a gravitational field. And an object will increase its gravitational potential energy if the height is increased. And if the mass, an object with a greater mass will also have a greater gravitational potential energy. So the equation for gravitational potential energy is E subscript P equals mgh, where m is the mass, g is the acceleration due to gravity, and h is the height of the object above the ground. So it's important to remember that gravitational potential energy is potential energy. It has the potential to be converted into other forms of energy, such as kinetic energy, if an object falls. So for example, if we have a book on a shelf, it has gravitational potential energy relative to the floor. And if it falls, that potential energy will be converted into kinetic energy. And that moves us on to the concept of kinetic energy, which is the energy that an object possesses due to its motion. It's defined as the work needed to accelerate a body of a given mass from rest to its stated velocity. And once that energy has been transferred to the object, it becomes kinetic energy. Okay, the equation for this is E subscript K equals half mv squared, where m is the mass and v is the velocity in meters per second. So the kinetic energy of an object is directly proportional to the square of its velocity. If the velocity doubles, its kinetic energy quadruples because of that square term. and it demonstrates the powerful relationship between velocity and kinetic energy. So one consequence of this is that when a car slows down and then stops, all of that kinetic energy has to go somewhere, and it will actually be converted into heat in the brakes. So again, because of conservation of energy, that energy has to go somewhere. So the next topic is power, and this is the rate at which work is done or energy is transferred, and it's a measure of how quickly energy is being used or converted from one form to another. The equation is power equals energy over time. The final topic then is energy efficiency, and this refers to the ratio of useful output energy of a system versus the input energy. And it's a measure of how well a device or system converts energy into work or the desired form of output without unnecessary waste. The equation that we use is efficiency equals 100% times useful energy output divided by total energy input. So that's been a video about energy and power. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.